In this module, we will consider Hooke's law and the work done by springs. Springs are a simple and useful mechanical device that provide a foundation for numerous more advanced physical principles. An ideal spring obeys something called Hooke's law, which states that the force exerted by a spring is proportional to the displacement of the spring from its equilibrium position and is in the direction opposite to the direction of the displacement. That is, F is equal to minus kx. Here, k is the force constant of the spring, and x is the displacement from equilibrium. So, consider our spring and Hooke's law, which is F is equal to minus kx. The end of the spring will be at some equilibrium position x naught, and we can rewrite Hooke's law in terms of this position as f of x is equal to minus k times the displacement x minus x naught. Now let's let the spring be connected to some object, and when the object is sitting with its edge at the equilibrium position, then the force of the spring on the object is going to be 0. Now, if we compress the spring a small amount, then the force when the block has moved to position x1 is going to be minus k times x1 minus x naught. But x1 is smaller than x naught, so x1 minus x naught is a negative number. That negative number times minus kx is a positive number. So we get the fact that the force is positive, and that is pushing towards the right. So the compressed spring will be pushing back towards the right against the compression. If we compress the spring a little bit further to position x2, then we get an even larger positive force acting towards the right. If we now extend the spring out to a positive displacement out to x3, x3 minus x naught is a positive number multiplied by minus k, gives us a negative force trying to pull the block back towards the left towards its equilibrium position. And if we extend it out even further to a larger displacement of x4, we get an even larger negative force. We can plot all of these in a diagram of force versus position, and what we find is that Hooke's law gives us a straight line passing through the equilibrium position, and the slope of this line is minus k. Now let's consider the work done by a spring. Assume the spring starts compressed at x1 and ends stretched at x3. How much work is done by the spring on the block? Well, we write out the work, which is the integral from the initial position x1 to the final position x3 of the force, which is minus k times x minus x naught times the infinitesimal displacement dx. The integral gives us minus 1/2 k times the quantity x minus x naught squared evaluated between x1 and x3. That is, we get minus 1/2 k times the quantity x3 minus x naught squared plus 1/2 k times x1 minus x naught squared. Now, if you don't know integral calculus yet, that's okay. We can also recall that we can evaluate this in terms of the area under the curve. So if we look at this, the work done between x1 and x naught is the area under the curve, which is going to be 1/2 of the rectangle, which has width of x1 minus x naught, and a height of the force, which is minus k times x minus x naught. So that is 1/2 of k times x1 minus x naught squared. That's that area under the curve. And it's doing positive work because the spring has a positive force acting on the block in this area, and the object is moving in the positive x direction, so we're doing positive work. Between x0 and x3, well, we have to calculate the same little bit of area, but this time we're subtracting it because the force is doing negative work between x0 and x3, because the force is negative, acting to pull back to the left on the object which is moving towards the right. Now assume the spring starts stretched at x3 and ends compressed at x1. How much work is done by the spring on the block? Again, we write out the work as the integral from the initial position, which is now x3, to the final position x1 of the force, minus k x minus x naught, times the infinitesimal displacement, dx. We carry out the integral and evaluate it, and we get minus 1/2 k x1 minus x naught squared plus 1/2 kx3 minus x naught squared. If we consider the positive term, that is the 1/2 k times x3 minus x naught squared, that's the area between the curve shaded in green. But this is positive work because the force is negative, but we are moving in the negative direction from x3 to x naught. So this does positive work on the block. Whereas moving from x naught to x1 does a negative amount of work. Finally, let's consider what happens if we assume the spring starts compressed at x1 and ends compressed at x2. How much work is done by the spring on the block in this case? Again, we write out the work as simply the integral from the starting position, which is x1, to the final position, which is x2, of the force times the infinitesimal displacement, work out the integral, and what we find is we do positive work from x1, but now let's consider going all the way to x naught so we can work out our area as easily as possible. So the area in green is 1/2 k times x1 minus x naught squared. But that's a little bit too much work because we didn't go all the way from x1 to x naught. We only went to x2. So we need to subtract from this the amount of work done between x2 and x naught. What we see is that in all of the cases, we simply get that the work is minus 1/2 k times the final position minus the equilibrium position squared, plus 1/2 k times the quantity, which is the initial position minus the equilibrium position squared. So the initial position always has the positive sign associated with it, and the final position always has the negative sign associated with it.